Evening, everybody. 5 o'clock on Thursday, so time for some Calculus 2. Tonight we're going to cover 6.1 using definite integrals to find area and length. And I'm going to start from a very basic step of what's called slicing when we do this, because it's going to permeate everything we do in this module. So I want to make sure we have a good foundational understanding. So today is going to be important from that point of view, in that we're going to make sure that we have a pretty good leave today with a pretty good understanding of what I mean by slicing and how we take a small view and then use a definite integral to encapsulate the whole thing. Okay. Let's dive into 6.1. We're going to look at area in a few different scenarios. And the first one we're going to talk about is area between two curves. All right. And again, I want to kind of come at it from this idea of slicing. So let's do a little better there. All right, so let's say we have two curves. We're going to go with the arbitrary sense first, just to kind of get an idea of what's happening. So we have some curve here. Let's call it f of x. We have some curve below it. It could be above it, below it. But for right now, we'll put it below. Call it g of x. And what we want to do is find the area between the two curves, between A and B. We want this area in here, right? Now, the concept is pretty simple based on what we know about definite integrals. The nice thing about a definite integral is it gives us the area under the curve. So basically, what are we looking at? All right, well, we know that the integral from A to B of f of x dx gives us the area under f. And we know that the integral from A to B of g of x dx gives us the area under g. So it's giving us this area, whereas the integral for f is giving us all this area. So the red just comes from taking the integral of f minus the integral of g. So from a conceptual standpoint, it's not bad at all. But I want to talk about it from a slicing standpoint. So we know the area we need is in between these two curves. And I want us to see it from a slicing standpoint because, like I said, slicing is going to permeate everything we do in this section. So I really want you to get the hang of it. All right, so let's talk about what happens with slicing. So with slicing, what we do is we focus in on a slice. Now we're looking for area. So I get one slice. Pretend like those are straight lines. My ability to draw straight lines is so-so on this thing. This is what we call the ith slice. All right, why the ith slice? Because it is some general slice. I could have put it anywhere in between A and B. All right, so we have a goal here. Our goal is to find the area of the whole thing. Well, what we've done by making the slice is we've narrowed down our goal, and it's to find the area of the ith slice. So we want to find A sub I. Now, basically what we would do is we would continue to slice this thing up, just like a Riemann sum, making a whole bunch of rectangular slices, all with the same width. They're all going to have a width of delta x. All right. Now, don't worry, we're going to do a few of these. Everything today I'm going to look at with slicing so you can get the hang of it. So the width of that slice is delta x. So if I were to pull out my ith slice, make it a little bit bigger. So there's our ith slice. The width of it's going to be delta x. Okay, that's great. Now what we're doing, the reason we use slicing is we assume that this slice is so small that we can assume that the top and bottom are straight so that our slice is just a rectangle. So the area of the ith slice would be the height times the width. We know the width, it's delta x. What we need is the height. Well, the height is going to come from taking f at this point. So let's draw, our drawing is getting a little crowded here, but we'll call this guy x sub I. So what we're going to do is we're going to calculate f of x sub I. That's the value at this point. And then down here, we're going to calculate g of x sub I. So the height ends up being f of x sub I minus g of x sub I. All right. Now I want to talk a little bit more about the sub I. Move that over so we got some more room for it. The sub I is in there because we are looking at a very particular case. We are looking at the ith slice. So what the sub I means is we're looking at a specific x value, but it's arbitrary. It could be anywhere in between a and b. So we represent that with x sub I. So basically, we're in a discrete case. We will turn it into a continuous case. Well, now we've got the height and width of our rectangle. So the area is f of x sub I minus g of x sub I times delta x. That's for just the ith slice. Well, what we do is then we approximate the area using a Riemann sum. The Riemann sum is going to go from 1 up to n of basically this. What we're doing now with the Riemann sum is we're summing up all these rectangles. This rectangle, this rectangle, this rectangle, this rectangle, this rectangle. Okay? So this idea is very similar, is the same idea as our Riemann sums. It's just we have the height between two curves instead of just a single curve. That will approximate the area. What we do to make it perfectly equal is we have to use infinitely many subintervals. All right? So we basically take the limit of this as n goes to infinity. And now we can say, well, that is the area because we're going to have infinitely many subintervals. That's going to basically cover up the whole interior of this region here. Well, once we do that, once we take the limit as n goes to infinity, that makes this a definite integral. So when we go to the definite integral, you'll see no longer do I use the sub i's. Because now we've gone from the discrete case to the continuous case. Also, I don't use the capital delta. I use a lowercase delta. It looks more like a lowercase d in my handwriting. Because again, this was a discrete case. This delta x was measurable. 0.25 units, 0.1 unit. It was measurable. This dx represents the infinitely small rectangle width that we deal with our definite integrals. Now, what are we integrating over? We're going from a to b. This is the same thing we had up here intuitively based off what we know of definite integrals. The reason I went through that is I want to start to get you used to this idea of slicing. I'm going to do slicing in several different examples today, tomorrow, or not tomorrow, sorry, Tuesday, and Thursday, and the following Tuesday. But I really want to get you in a situation where you're comfortable. We're good with definite integrals, and you've probably done area between curves before. So the topic isn't new, but what we have now is how we can use slicing in order to create a definite integral. In this first lesson, in 6.1, it's not going to be all that important. Because now that we have the formula, we're going to go ahead and solve this. And we'll do an example here in just a second. But later on, when we get into 6.3 and 6.4 in particular, slicing is going to be a really valuable tool to make a big problem smaller. So I like the idea of getting you used to slicing in a familiar context so that later, in a week or two, you'll be able to use slicing in more complex contexts. We're assuming they're all of the same width, but not the same height. And that's where the f of x sub I and g of x sub I come from, because these are going to change depending on what value we put into the function. Because they'll be the y values of this function and the y values of this function, so they'll change as we go along. But we do assume that they all have the same width, because eventually we're going to let that width basically go to 0. It's infinitely small, and so we're fine to allow them to be the same width. But let's just say we were over here, on our Riemann sum. What we would do is, we plug in 1 here and x sub 1. So maybe we would use, this x value for our first height. And then we go to x sub 2, x sub 3. We would keep going. That would be the discrete case. And what we would do is, just like when we were doing numerical integration a couple weeks ago, we would put each of these inputs in, get the difference in outputs. That would be the height of each rectangle, add those up, and then multiply by the common width. Now, here's where this is really cool. What happens when we go from here to here, and it's why the sub i's go away, is this is the continuous case. So what the definite integral does is it does this for every single x value between a and b for us. And that's why we don't have to plug anything in. It's taken care of. And, where are these sub i's coming from? It's kind of like, this left-hand side is what we were doing a couple weeks ago with numerical integration. But we're using this idea of slicing to actually create a definite integral. And so that ends up being all we have to solve. Okay, let's do an example. And like I said, now that we know how to do this, when you're doing area between two curves, you won't need to do slicing. We're going to look at see how we can kind of simplify this for area between two curves. Oops, don't want to do that. There we go. Okay, so let's just say we pick a couple curves. I've got a couple already here in Desmos. We'll do a couple examples. We'll do one in x and one in y. Let's say we want the area between y equals 4x and y equals 6x squared. Well, we can see the area right here. And basically, when you're doing area between two curves, notice f of x was on top, g of x was on bottom. So that's really all we need to observe, is which one's on top and which one's on bottom. So to set this up, let's do it in a different color. So we're looking for the area between y equals 4x and y equals 6x squared. And they've got a naturally bound area. And we can see the linear functions on top, the quadratics on bottom. So we don't have to do the slicing on this. You can, you absolutely can, but we built the formula. We know that it's top minus bottom. So 4x minus 6x squared dx. And now all we need are our limits. Well, the limits in this case are going to be the intersection points. We got 0, 0, and 0.66, 2.66. All right, well, let's talk about where those are coming from. How do we do those algebraically? Well, remember, the intersections are where these two graphs are equal. So we can set them equal to each other. 4x equals 6x squared. And we'll solve this for x. So we can bring the 4x over. 0 equals 6x squared minus 4x. Factor out an x. And you can factor out a 2 as well. It's up to you. 6x minus 2 minus 4. I did not factor out a 2, so let's keep that. Equals 0. That's going to yield 2 points. X equals 0. And x equals, this one here is going to give us 2/3. Add the 4 over, divide by 6. So 4/6 is 2/3. This is in terms of x, so we're going to go between the two x values. So 0 to 2/3. In module 1, we focused plenty on solving definite integrals. This section is more about setting up definite integrals to solve applications. So most of the examples that I do in here, I'm going to set up but not solve. We have all the, we have all the techniques for solving them algebraically. You got Symbolab. So I'm not going to worry about solving them because that way we can get through more stuff because we've already covered solving them. So a lot of times you'll see me set them up but not solve them because we've had practice at that. But when we get the area between two curves and we've got a clear top and a clear bottom, it's top minus bottom, and then we find our endpoints for our integral. Questions about that example? All right, let's do one more area between curves. I'll pull one out of the book here. Let's see. We're going to do one now where it's in terms of y. All right, so let's turn those off. Desmos can do these in either form. So if you were to do these in your calculator, just do them as parametric equations. So x equals 1 minus y squared. So we're going to do b here. We get a sideways parabola, the first one. Second one's also a quadratic, so we're going to expect another one. X equals 2 minus 2y squared. And we see that we have an area between the two of them. All right. So now, if I were to take a slice, we got to think about how this changes things. Notice, and as the idea I'm going to talk about now, when I talk about top and bottom and left and right, that's something you'll hear, for those of you guys who take Calc 3, especially with me, it's something I really like to emphasize with integrals, because it comes up a lot. And what do I mean by that? Now, on the previous graphs, let's turn these off for just a second. Over our region, we had a very clear top, we had a very clear bottom. This also had a very clear right and left, so we could have done this one in terms of x or y. Wouldn't have mattered. Here's where things get interesting. Notice here that the top and bottom is different over here than it is over here. So if we tried to do a top and bottom method, we absolutely could, but we'd have to break it into 3 separate intervals. One from 0 to 1 on up here, one from 0 to 1 down here, and then one from 1 to 2 because the top and bottom are different in all three of those sections. Yeah, you could use symmetry between here and here, but if we were integrating over a function, that wouldn't work. So there's actually a quicker way. And what we do is we make our slice in a different direction. So we make our slice, let me try that again. So we make our slice now in a horizontal direction. So there is our ith slice. And here's where things get interesting. Instead of a delta x, this is in the y direction, we would say it has a delta y. And then again, you know, we could draw in more slices, but all we need is one slice. So delta y is going to be the width of our, or the height of our slice. The width is going to come from this guy minus this guy. So if we call the, let's say we call the black function f of x, excuse me, not f of x, f of y, and the purple one g of y, well, this one is larger. So f of y minus g of y is going to be the width. So when you're doing it in terms of y, you do right minus left. And that works perfectly here because we got a clear right and a clear left. So to set this one up, let's put our functions on here. X equals 2 minus 2y squared. X equals 1 minus y squared. Identify which one's which. Which one of them goes out to 2 in the x? Well, that's this one. So that's our right. That's our left. Guys, our integrand is set up. 2 minus 2y squared minus 1 minus 1y minus 1 minus y squared dy. Because now we're integrating with respect to y. Questions about setting up the integrator? Right minus left. Okay, last thing we have to talk about is our limits. In the previous problem, our limits were between two x values. Now we're integrating with respect to y. Our limits should be y values. Graphically, we can see pretty clearly our limits are negative 1 to 1. But if we wanted to verify that, we do 2 minus 2y squared equals 1 minus y squared. And we solve this. So we can add 2y squared to both sides. Subtract 1 from both sides. We get y squared equals 1. Square root of both sides, we get y equals plus or minus 1. So for finding your limits, they can be done graphically or algebraically, whichever you find easier. Sometimes when they come out to nasty decimals, you might be better off doing it algebraically to get the exact values. But as long as you're keeping enough decimal points, you should be fine using either. So again, if we have a clear top and a clear bottom, we keep everything in terms of x, and we set it up top minus bottom. In these cases where we don't have a nice clear top and bottom, or it's not the same top and bottom. Maybe I shouldn't say clear. It's not the same top and bottom the whole time. See if you can do it in terms of y. You know, that would require you having both functions in terms of y or getting them in terms of y. And that's really the only difference, is now we're integrating with respect to y. So for area between curves, you don't need to do slicing. If you want to practice slicing, it's a good opportunity, but it's not necessary. All right, questions about this one, about area between two curves? All right. I think the next ones are really cool examples of slicing. They were in the lesson, but I like to go through them with you guys to see what kind of questions you guys might have, because it's not necessarily trivial. And We're going to do it with areas now. We're going to do it with volumes in the next section. So, like I said, my goal is to get this idea of slicing down. And it's going to come from basically this idea. Now, let's say we have a triangle. Let's give this triangle a base of 10 and a height of 5. All right. Simple question for you guys. What is the area of this triangle? Nothing crazy going on there. Half base times height, right? All right. Now, what I want to do is I want to approach this thing with this idea of slicing. All right. I'm going to do a vertical slice, or excuse me, a horizontal slice that is perpendicular to the bottom. This is my ith slice. Now remember, I'm drawing it big because I want to be able to write on it. But this is basically any slice in the triangle. It's an arbitrary slice, why we call it the ith slice. And the only reason I'm writing it so big is so I can draw on it. But the idea is we make this slice so small that I can assume that these sides are straight up and down. Okay, because that gives me a rectangle, and rectangles are very easy to find the area. Triangles are too, and we have a base and a height. But again, we're building towards bigger things later in this module. All right, we got to give that thing a height. Let's call it delta H, because every slice would have the same height. All right, so if I was to make another slice here, that one would also have delta H. If we were to make another one down here, so on and so forth. Pretend like those are equally sized. I apologize for my terrible handwriting. That would have a height of delta H. So all the slices have the same height. Okay. Now, that's part of what's behind this concept. Again, all we're doing is building Riemann sums. Okay. Now, here's a question for you guys. Depending on where I put the slice, so if I were to put the slice down here, we know they're going to have the same height. Do those slices have the same width? And I know it seems very trivial. Guys, this is going to be an important idea going forward. If a slice varies, if any length, width, or height, or any dimension of a slice varies in your object, it must be denoted with a variable. So I'm going to call this guy W sub I for the width of the ith slice. All right. The W sub I tells the viewer that this varies. Because if I were to put the slice down here, it'd be much wider. If I were to put it up here, it'd be much narrower. All right, now here's how this goes. Same as last time. Area of the ith slice. Well, it's just a rectangle. Width times height. W sub I, delta H. All right. Now, based on what we saw last time, we know we're heading towards a definite integral. Well, last time when I did this, let me just go back and show you. The x sub I and the delta x matched. In other words, they were the same variable. Like I said, not a big deal now, but when we get into more complicated cases, this is going to be one of the things I want you to look for. If these do not match, we need to find a way to make them match. So how do we do this? There's going to be a few different ways depending on what your object is, but we need a relationship between W sub I and delta H. We want to get, we want to get W sub I in terms of H sub I. Well, what's H sub I? Well, H sub I is going to be the height that of this triangle created by our W sub I. Okay? The reason that is so important, redraw it over here. What we have now are similar triangles. When you have a triangle inscribed inside another triangle, they are what are called similar triangles, and the ratio of their sides are proportionate. You're going to see similar triangles show up a lot in this module. So that's why we're doing one that involves similar triangles. So you know to look out for. What does that mean? Well, that means W sub I is to H sub I, the ratio of those sides, as the width of the big one is to the height. This will allow us to get W sub I in terms of H sub I, because we can cross multiply by H sub I. And we can simplify a little bit. W sub I equals 10 over 5 is 2 H sub I. Guys, like I said, as I'm going through this, feel free to ask questions. I know you saw this in the lesson, but this is important stuff, so I really want to make sure you feel comfortable. That is going to go in for that guy right there. So now A sub I becomes 2H sub I delta H. We check the area of the ith slice. The variables are compatible. We're ready to go to our definite interval. Now I'm going to write it up as a Riemann sum this time, but guys, you do not have to. We're trying to get to the point where we actually can skip this step. So we won't do this every time. But I want you to see the transition, what's happening. At least on these first few examples. So n equals 1 to infinity. Excuse me. I kind of could have put that in there to begin with, but since I put the limit out front, let's do this. I equals 1 to n of 2h sub I delta h. So we go and we write up our definite integral. We no longer need the sub i's. And that delta h becomes a dh. And the last thing we need are limits. Well, remember where h came from. H is the distance from the top of the triangle to our slice. So we need to think about the smallest h can be and the biggest h can be. What's the smallest and biggest h can be? Smallest h can be is what? You guys can throw. It's a really weird way to think about 0, but there is this infinitely small slice that lives at the very tip of our triangle, and that's when h is 0. And then we also have an infinitely a slice here at the bottom. And what's our height here at the bottom? What's the largest h can be? So h can go from here down to here. So the biggest h can possibly be, what it takes for h to get to that bottom slice, I don't know why that many keeps coming, is 5. Does that make sense? H is going to range from 0 to 5. That's what's going to give us every slice in the triangle. This one we are going to solve. Antiderivative of 2h, h squared, from 0 to 5. End up with 5 squared minus 0 squared. No surprise. There's our 25. Now, again, we get a triangle, we're going to do half base times height. But this is just to show you the power of slicing and how we can find areas of different figures. This will work in a lot of different contexts. Questions about this? All right, let's look at one more on slicing. Let's do a circle. Again, this one was in the online lesson, but it's a good one to look at. And like, that's a circle. All right, so we have a circle, and this time we're going to actually derive the formula of a circle. Let's do it in general, of radius r. Actually, let's make it capital. All right, so that's the radius of the circle. So how do we do this? Well, we make our slice. You can do it horizontally or vertically. And one thing sometimes that's easier on the circle, and this is kind of user preference. If you want, you can put it on a set of axes with the origin being at the center. Might make it a little bit easier to deal with until you get a little more used to it. So this would be our x-axis, this would be our y. So we have some slice here. It's not a very good looking slice. It's most of mine. But we see we've got a height of delta y. All our slices would be of the same height. All right, well, this distance here would be x sub I. So we can already take our slice, and so I'm going to move that because I'm going to want to put something else there in a second. All right, this right here is x sub I because it's some x value away, it's some distance x away from the origin. Okay. And similarly, you know, the height of our slice here would be y sub I. You know, is there some arbitrary point where we decided to put our slice? I draw it a little bit thicker so I can write on it, but kind of, you know, we're assuming the slice is so small that, hey, we can assume it's rectangle, even though it's the sides are made out of the circle. All right. Well, the nice thing is this makes our area of the ice slice easy. Now, it's obviously going to be a height of delta y. The width, because we got to get the whole thing in there, is actually going to be double x sub I delta y. All right, because we need to account for this guy too. That length there is also x sub I. All right. At this step, I know we only talked about this once, but what should we notice? We want area. So we're only, you know, our next step is to do our definite integral. But before we do that, what should we notice about our a sub I here? What should set off an alarm for this? Two variables. Perfect, Taylor. This thing's in terms of delta y. This thing's in terms of x. We want everything in terms of y. All right, so how do we do this? We don't have a triangle this time. But here's what we do have. This is going to be another relationship that you're going to see in this section. Remember that this distance here is the radius. This distance here is x sub I. This distance here is y sub I. We have a right triangle. So we know, because of the Pythagorean theorem, x sub I squared plus y sub I squared equals capital R squared. Remember, R is a constant. This would be given in the problem. This would be a circle of radius 5 or 7. We're just doing it in a general term. We want to sub out x sub I and put in y sub I. So we're going to solve this for x sub I. So x sub I squared equals r squared minus y sub I squared. And then we'll square root both sides. So there is x sub I in terms of y sub I. That'll get plugged in right here. So we now have 2 times the square root of r squared minus y sub I squared delta y. Our variables now match. So we are ready to set up our definite interval. Like I said, I'm not going to do the Riemann sum this time. We have 2 square root of r squared minus y squared dy. And the last thing we need are our limits. Well, how do we find our limits? Well, y is our variable. So we need to think about the lowest y can be and the highest y can be. Well, remember, this is the distance from the center out to the edge of the circle. That distance is r, and same with that distance. So it's going to go from negative r to r. Remember, these have to be constants, and r is a constant in this case. Now, calculating this will give us the area of a circle. We know the area of a circle, right? Pi r squared. We learned that one a long time ago. So what I'm telling you is this comes out to be pi times, in our case, capital R squared. I'm not going to work through this one right now because I got other stuff I want to do with you guys. But if any of you guys are up for the challenge of proving that this is equal to this, I will give you some extra participation points for it. That would just be due sometime before our next class meeting. You can take a picture of your work and email it over to me if you want. This is 100% optional, but think about what our integral looks like. What technique of integration are we going to need to solve this? Remember, r is a constant. So we have some constant minus y squared under a radical. Do you remember what technique of integration we used for that? I know it's been a few weeks, but it's good to start reviewing this stuff as we get closer to the end. All right, I'll give you a hint. It'll be a trig sum. So, again, if any of you guys want to try this, feel free. It's actually pretty cool. It's good practice. I got other stuff I want to make sure I get time. I want to make sure we have time for today. But if any of you guys want to solve this, by hand, create a proof. Start here, end up here. All right. Okay. That aside, any questions about the slicing? Sorry, my drawings get so messy. I'm not the best with the drawing on these whiteboards still. But what I want you to take from this is this idea of we take a figure, we look at a slice instead of the whole figure. We figure out, okay, how do I figure out the area of that slice? Then we use a definite integral to get the area of the whole figure. That's essentially what we're doing. I'm not gonna tell you guys which trig sum. You guys are gonna have to figure that out. But you're right, it's gonna be a sign. So yeah, guys, feel free to try that. If you finish it between now and next class, just shoot it over to me. I'll take a look. It's actually pretty cool. All right. So again, these were both in the online lesson. So a little bit of repetitive, I know, but I really wanted to go through them with you. All right. Next up, arc length. So, oops, I don't think I had this thing ready. Give me just 1 second. Just so this doesn't take, oh, good, perfect. Perfect. All right. Now we talked about the beginning of this. We've reviewed polar coordinates, so we're not going to worry about that right now. We are talking about arc length. Oh, sorry. Area of polar curves first, then arc length. My fault. I want to do area of polar curves since we're in this area topic, and then we'll talk about arc length. Okay, so area of a polar curve comes from the area of a sector. Well, what's an area of a sector? It's 1/2 r squared times theta. Well, all that really is doing is taking what percentage of a circle we're looking at, because we know there's 2 pi radians in a circle. If you put 2 pi in for theta, well, the 2 and the half cancel, you get pi r squared, which is the area of a circle. That's all the radians are doing, is they're giving you what fraction of the circle you're looking at. So what we're going to do is we're going to use this to figure out how to do the area of a polar curve. And here's the basic idea. So we have some polar curve r equals f of theta. And we want its area between, let's say, angles alpha and beta. Okay, so we want this area, and what we do is, guys, is going to sound really familiar, and you're going to be sick of me saying it in a week or so. We break this up into slices. The only difference now, instead of them being rectangular, there are a bunch of sectors. All right, a bunch of sectors, all with the same angle. So they all have an opening of delta theta. All right. So what happens is, we compute the radius on in each little sector. So the area of each sector is 1/2 times the radius on that sector times delta theta. Well, then to get the whole thing, we got 1/2 r d theta. 1/2, sorry, I forgot the square. 1/2 r squared d theta from alpha to beta. That's basically where this formula for polar comes from. Guys, you're not going to have to do polar curves with slicing. We have the formula now. All we need to know is how to use the formula. So let's do a couple examples where we have to use the formula. For instance, let's find the area of 4 leaf rows. So r equals cosine of 2 theta. Now, this is going to be something where you can leverage things like Desmos, excuse me, to figure out your limits. So there's our 4-leaved rows. And if we're not sure on the limits, well, let's see how this thing is generated. All right, so starting at 0, we come around and we'll be at pi at about 3.14 roughly, right? So 3.1. We can see that already makes half the curve. If all we're doing is area, we can absolutely use symmetry. But check this out. This rows gets completed at 2 pi. That's our limits. Watch how straightforward setting this up is now. So A equals 1/2 times r, which is cosine of 2 theta squared d theta from 0 to 2 pi. This thing is set up and ready to go. Now, like I said, I'm not going to solve these right now. We still have some more stuff we got to go through. But remember, we dealt with cosine squared earlier this semester by hand using a trig identity. So to do this one by hand, we use a trig identity to change it from a cosine squared to a cosine, and then do our integral from there. All right. But setting these up is not bad. You got this formula right here to use to set them up. Questions about this first one? All right, here's the next one. Area inside of R3 cosine theta and outside R1 plus cosine theta. This is going to be one where we want to see the graph, okay? Because there are three areas here. There's one here, and one here. We got to figure out which one we're looking for. Well, we want it inside this guy and outside of this guy. Well, which one is which? Well, this one goes all the way out to 3, so this guy here is our red. This is our green. So we're looking for this area right here. All right. Now, I'm going to start to set this thing up, and then we're going to talk about the limits second. Because setting this up, area between polar curves is just like doing area between two curves in rectangular. We're going to do the bigger minus the smaller, but we have to observe our formula. All right. So let's do this one in a different color. All right. So our bigger one we know is R equals 3 cosine theta. Our smaller one is R equals 1 plus cosine theta. So we can, guys, setting up the integrand is not bad. If you want, they're both going to get multiplied by a half. So you can put the half out front. Then you got your bigger R, 3 cosine theta squared. And then we subtract out the smaller part, because what we're doing, we're not going to get the whole area of the big one, subtract out the area of the small one. So 1 plus cosine theta squared. Our integrand is set up and ready to go. The only other thing we need are the limits. Okay? So let's talk about finding the limits for this guy. Now, as we saw before, to get limits, actually, no, let's just say, to get limits, we set the two curves equal to each other. Same thing goes for these. 3 cosine theta equals 1 plus cosine theta. Okay, so subtract cosine theta from both sides. And we get 2 cosine theta equals 1. And divide both sides by 2. We get cosine theta equals a half. All right, so guys, this is nothing more than our unit circle. So at what angle in radians, at what angle in radians is cosine equal to a half? You guys remember? I know it's been a while. I keep asking you to remember way back in the unit circle. And there's two places. Cosine, as a reminder, is positive in the first and fourth quadrant. And cosine is 1/2 at pi over 3. Now, a couple of different things we need. Now, pi over 3 is going to be that first quadrant angle. Now, when we think about this, we're going to look at these angles here in a couple of different ways. There's a couple of different ways to think about this fourth quadrant angle. It could be, 5 pi over 3, or it could be negative pi over 3. Those are the same angle as far as trig goes, but they're not going to yield the same definite integral. So this is where we can use the graph to do some exploration. So let's take a look at how we can do this. All right, so let's get our two curves on there. There's one, here's the other. Get them in a place where you guys can see them. Okay, now here's what I mean by this. All right, we know one of the angles is pi over 3. So what I'm going to do is set the lower angle to be pi over 3 and see how that changes my curve. Oh, we got to change it here too. All right. And we'll do the same on, shoot. All right. So one thing we should notice, like we probably noticed right away, is that's giving us this part. We know we wanted this crescent moon. So let's see. Let's put in the negatives. And we're going to go up to pi over 3. That's what we want, is that crescent there. So there's our area. This is a great way of confirming your limits. Your graph should look like the part you're looking for. That tells us, without a doubt, that our limits are negative pi over 3 up to pi over 3. Okay? So two things will go into finding your limits on this. Number one, setting your two polar curves equal to each other so that you can see what angle they intersect at. And then which is what we did down here. And then number two, look at the graph, because if we had gone pi over 3 to 5 pi over 3, we'd be getting this side over here. It's not what wasn't the area we were trying to find. All right, so even though 5 pi over 3 and negative pi over 3 are technically the same angle, as limits, they don't yield the same definite integral because it causes cosine to go through different values if cosine has to go this way versus going this way. Questions about this? So area between polar curves is not hard to set up. The integrals can be a little tricky. You know, this one, you'd have to square everything, combine like terms. You'll likely end up with a cosine squared term, which we know how to handle via substitution. So, you know, if you're working on it on a homework problem or something, you might want to try to do it a little bit by hand. But hey, if you get it on a take-home problem, use Symbolab or Wolfram Alpha. Okay, questions about area of polar curves. All right, one more topic to talk about. Arc length. Now, the derivation of arc length is in the online lesson, but I just want to show you, it's once again, it comes back down to the idea of slicing. So, you know, if we're looking for the length of a curve, let's say we're looking for it from A to B, what we do is we basically represent that with a straight line. All right. And now that straight line has basically a delta x and a delta y. Said those backwards, but then I'm right. Then the way that I'm writing. Okay. And so this is our ith slice. So L sub I, based off our Pythagorean theorem, is the square root of delta x squared plus delta y squared. All right. Now, here's where we involve our derivative. Remember that our derivative is a rate of change. It is essentially the slope of this line at this point. This blue curve here, let's give it a name. It's y equals f of x. And what we do is we calculate the derivative at this point. We'll call that point there x sub I. That would give us the rate of change, and the rate of change times delta x approximates delta y. So delta y is approximated by f prime of x sub I f prime of x sub I delta x. This is where the derivative gets introduced into this thing, because we're going to substitute this into here. Again, this is going to be, right now we're looking at the discrete case, the ith case, and we use a definite integral to generalize. So L sub I becomes square root of, this is not something you guys need to know. I just want to show you where it comes from, because I do think it's actually kind of cool. Put in that parenthesis a little too soon for what I wanted to do. Delta x, that whole quantity is squared. Now what we'll do is we'll put that square on both the on both those terms. So we're going to distribute the square. So squared, squared. That allows us to pull the delta x squared out of those two terms. So we end up with 1 plus f prime of x sub I delta x squared. We can split up a square root over multiplication. So we get square root of 1 plus f prime of x sub I. I lost my square here. Sorry about that. Squared. And then this part's just the square root of delta x squared. And that's basically where our integrand comes from. Now, I know I went through that kind of quick, but it is in the online lesson. I just wanted to show you that it's still this idea of breaking something big down into a small piece, focusing on that small piece, then creating a Riemann sum to make it definite. All right. Now that you have the formula, don't worry about this. This is just the derivation. So how do you use it? Well, let's take a look. So our f of x is x to the 3 halves. And we're going from x equals 1 to 3. So, and here's the biggest thing, and I see it all the time. The biggest thing is some people forget to take the derivative first and just plug in f of x. So find your f prime first. Equals 3 halves x to the 1 half. That gets plugged into the formula. Square root of 1 plus 3 halves x to the 1 half squared dx. And our limits are right here. And now we're into calculating this thing. So we can simplify a little bit first. Both these get squared. 3 halves squared is 9/4. X to the 1 half squared. 1 half times 2 is 1. Dx. Now, again, I'm not going to solve this one. This one can be done with a u sub. This one's not too bad. One of the things I will mention about arc length is because of this square and the square root, the definite interval for arc length for some functions and for a lot of functions can be pretty messy. So there will be some that you might want to use Symbolab or Desmos for. But any of these that come out to the first power is a simple u sub. If it had been a squared power, we could do a trig sub. But past that, they do get pretty messy. And when they do get messy, we do use technology. Okay. So that does happen in a lot of arc length problems. So I don't want you to, get frustrated over some of the messy definite integrals you see with arc length. Some of them are just going to need technology to solve. It's just kind of the nature of the beast. But now that we have the formula, that's all we got to do is use that. Okay. Questions about this one, about arc? All right. Here's what's nice. Now that we got that, arc length for parametric and polar actually just kind of follow from it. Again, this is in the online lesson. Let's see. Yeah, let's go ahead and take a look at how we derive it. All right, so we just saw the arc length formula right here. I'm going to write it up just a little bit differently. And, we're going to go from A to B. And we have 1 plus, now instead of writing f prime, we're going to write it as dy dx squared dx. All right, we use a nice little chain rule trick to make this work. Again, guys, this isn't something you need to know, but I do think it's pretty cool to see how you go from one to the other. So we'll leave that alone for right now. What I'm going to do is rewrite the dx. Actually, no, I'm not going to rewrite the dx. I'm going to add something. So we got the dx, and then I've got dx dt times dt dx. So I haven't really changed anything I have. But you can kind of see, hey, if I wanted, if I canceled the dx's and the dt's, I still have dx. Okay. Now, what we're going to do is we're going to take the dx dt and put it under the radical. So a to b of 1 plus dy dx squared. And if I put the dx dt under the square root, I have to square it. And I'll explain that here in just a second. So you guys can follow me. You got the dx dt dx. Well, remember, we can split up a square root over multiplication. So going the other direction, going from here to here, I'd have the square root of dx dt squared, which would give me this dx dt. Okay, now we're going to distribute that over the parentheses. And that's going to give us dx dt squared in the front. Here's where it gets a little interesting, but bear with me. Right now we have dy dx squared times dx dt squared for this second part. And then check out what happens here. The x's cancel. There's our dt, getting us over into parametric. One last thing we have to do, and this is something we talked about in parametric. We have dx dt squared. Remember, this can be rewritten as dy dt over dx dt squared. Well, what I'm going to do is I'm basically just going to square each of these. So since the whole fraction is squared, we can square the top and the bottom. So dy dt squared over dx dt squared times dx dt squared. This, again, guys, it's not something you have to know, just a little Where does it come from? There is arc length for parametric. Okay. You guys actually did arc length of parametric when we did. You didn't do arc length, but you did the integrand of arc length when we did the worksheet on parametric, because this was the speed. So the arc length is integrating over the speed. All right, one more to show you, and that's for polar. Now that we have parametric, going to polar is really easy, because all we're going to do is this is going to be dx d theta, dy d theta from alpha to beta. Okay. Now, because this isn't always the easiest way, here is an alternative form for arc length and polar. So it depends on which route you want to go. I'm not going to do the derivation on that because it does take a little while, and I know we're kind of running low on time. But to go from this derivation to this derivation, we use our transformations, and that is that x equals our cosine theta, which would be f of theta cosine theta, and that y equals our sine theta, which is f of theta sine theta. All right. And so now you can do your dx d theta and your y d theta, both which involve the product rule. And then there's a little bit of algebra. But because a lot of times our, sorry, didn't mean to do that. Because a lot of times our polar curves are given in terms of r, so like our two lead rows. So like r equals cosine of 2 theta. It's much easier to do this form because now what do we need? Well, we need dr d theta, which is the derivative of this guy, which is a chain rule. So it's going to be negative 2 sine of 2 theta. And so now we can set up our integral. Square root of cosine of 2 theta squared plus negative 2 sine of 2 theta squared d theta. Unfortunately, because of that 2 in there, this won't work out to be a nice Pythagorean. I couldn't have that 2 in there. So actually, let's do that. And from alpha to beta. But let's do one last thing. Okay. Now, let's look at the curve first, just as a reminder. Last example, and then get a few minutes for some questions. Oh, there's one other thing I wanted to show you, actually. So I'm glad we came back to this. Let's turn this off for a sec. Let's go back to these guys. When we were doing this, let's get the whole curves out. There's one other thing I want to show you in Desmos in case you're not aware of it. When you're trying to find out the limits, another thing that can help you, to go to the wrench up here on Desmos, you can change to a polar grid. And now we can see that that angle is pi over 3, and that one is pi over 3. Now, they won't always land perfectly on one of these rays, but well, when you're dealing with polar curves, that might be something you want to use to help you out. All right. All right. Last thing. This is pretty cool. All right. R equals cosine theta. We're going to keep it basic. All right. So if we look at what we have here, we have a circle of radius 1/2, right? So here's what we are going to do. We're going to run it through that arc. So our function is r equals cosine theta. Dr d theta is negative sine theta. We can see very clearly we have a circle of r equals 1/2. And remember what we're doing arc length. Arc length, let's calculate the arc length of the entire curve. Now we're doing this for a very specific reason, because we know how to do the arc length of a circle, right? The circumference of a circle is 2 pi r. 2 pi times 1/2, or pi. All right, let's see what happens here. So, and also, something else to notice. Check out here that our limits are just 0 to pi to get all the way around the circle. If I go to 2 pi, I don't get anything different. Because I'm just going around the circle twice. See how it's thicker? So that 0 to pi is enough to get around the circle. Why is that important? Well, that's going to tell me that my limits to get around the circle for the curve are just 0 to pi. And then we use our formula. So cosine of theta. We know what the answer should be. Let's see if it comes out to be that. Negative sine of theta squared d theta. Check out what happens here. 0 to pi, square root of cosine squared theta. Negative sine times negative sine is positive sine squared theta d theta. Well, gee whiz, that's our Pythagorean identity. So sine squared plus cosine squared equals 1. So we have the integral from 0 to pi of the square root of 1 d theta. Square root of 1 is just 1. So the antiderivative is theta from 0 to pi. Get pi minus 0, or pi. Once again, it's something we already knew from our basic math, but we're verifying it using integrals.